Uh, Hello, everyone. Thanks for joining me today. My name is Sergey. I'm software engineer at Datadog. And today I'm going to talk about subsetting in gRPC. So to give everyone a little bit of context, I want to start with a very quick introduction of load balancing in gRPC and how it's related to the topic of subsetting. So as many of you probably know, on the client side, gRPC can act as a load balancer. And what it means is that every client takes the list of available servers from a service discovery system, which is usually DNS, and then it decides how to distribute a request across available servers. So the simplest possible load balancer in gRPC is called pick first, and what it does, it just sends all requests to a randomly picked server. So now, if you decided to look pick first, the problem you might see is that the resulting request distribution end up being very uneven, as you can observe on this graph. And as you can see from this slide, it kind of makes sense because statistically, the probability that every server will be picked exactly the same number of times across all clients is very low. So the way you can deal with this is by using a different load balancer, which is called round robin, which works very differently. So what it does, it establishes connections with every available servers, and as you can see, the resulting request distribution end up being almost completely and perfectly even. So round robin is not a silver bullet though, because it has its own challenges. And the major problem with round robin is the number of connections it creates. So those connections are mostly cheap, but not exactly free, and you can see, especially you can see this overhead with TLS. So another issue is that it perfectly balances request, but not server-side load, which is the metric most of the people care about. And the last problem is that just because how many of those connections it manages, it makes every connection very poorly utilized, which makes it very hard to get meaningful client-side statistic per connection. And I'll talk about why this is a problem later in my presentation. So now let's introduce subsetting. So subsetting is an alternative load balancing strategy, and basically what it does, it picks a subset from all available servers and then distributes requests across them. So one useful way I like to think about subsetting is that it's something that sits between two extremes, pick first and round robin. So with subsetting, number of connections you manage is way less than with round robin, and you can directly tune this value by setting subset size. But at the same time, you have the flexibility to shift requests between chosen servers in ways to minimize load imbalance across servers. So let's talk about how this can be implemented and what we tried. So before we dive into details, I want to briefly mention a design goal we set for ourselves. So we want all our new features we develop to be as close to zero config as possible. And the reason is that if we manage to do this, this is going to be win-win for both us and our users. So we maximize the impact we provide across all servers in our organizations, and our users don't need to care about low-level details such as connection management. So let's get back to subsetting. So one way to implement it, which is an obvious one, is to do a fully random subsetting, which means every client just picks n random servers out of the list of available servers. So one problem with this is that this potentially could lead to high connection churn during server rollouts. So imagine what happens if a server got deleted, like is illustrated on the bottom diagram. So at this point, every client recalculates its subset, and the probability that it will pick exactly a similar subset is very low. And in red, I marked all new connections, and in green are connections that are being preserved. And as you can see, most of the connections are completely replaced, which is something we want to avoid. The trick we use to deal with this is to use a technique called rendezvous hashing. So the way it works is by this. So on startup, every client creates a random value, which we call seed, and then it uses seed to compute a hash for every server using server IP address. So given a seed and server IP, the hash is stable. So then our load balancer sorts all servers by hash and pick first n servers from the list. So as you can see, if a server gets deleted, this does not affect hashes for other servers, as the IP addresses and seeds are stable, and connections are kind of sticky, which is exactly the property we need. So this diagram illustrates the effect of tuning different subsetting parameters and what resulting connection distributions we are going to have. So the main takeaway from this slide is that the amount of imbalance you are going to have is directly correlated with the average number of connections your servers expect. So on the top slide, you can see that the average number of connections is close to 5 and distribution is terrible. But on the bottom slide, average number of connections is close to 1,000 and it looks kind of tight. But the bad news here is that average number of connections per server is exactly the property we are trying to minimize. So there are some trade-offs here. So we applied random subsetting to a few random apps in our infrastructure, and as you can see, the results were great from perspective that resource utilization on the server went down a lot, but at the same time, load distribution on the server became a lot more imbalanced. And if you wonder why we care about this so much, this is because service owners need to scale their deployments to account for the worst case. And this directly correlates with cost. So this is not ideal. So we explored alternative approaches and we tried to use deterministic subsetting and engaged with gRPC community trying to contribute this. So TLDR of deterministic subsetting is this. It's a technique that requires coordination between clients. So clients can choose their subsets in an optimal way such that they can minimize both connection churn and server-side load imbalance. So on this slide, I highlighted two most popular implementations we found of the internet. One deterministic aperture from Twitter, another one from Google. And if you're really interested in this topic, I can mention that my current colleague, Ruben Oanta, is currently here with us today, and he is the author of Twitter aperture implementation, so I'll be happy to connect you with him if you have a lot of questions about this. But the reason I just mentioned this so briefly is because this idea didn't fly. So basically the response we get is that deterministic subsetting requires coordination. And there is a standard way to do coordination in gRPC, which is XDS. And if you use XDS, you can as well just calculate your subset on the control plane and then feed every client its own subset. So alternative way of doing coordination between clients won't be accepted by gRPC project. So we went ahead and explored different options. What if we just run random subsetting and then use something on top of it to correct the imbalance generated by random subsetting? And an obvious candidate here is a gRPC load balancer, which is called weighted round robin, or WRR for short. So this is going to be important in later part of my presentation, so I'm going to explain the mechanics of WRR a little bit. So WRR relies on server-side load reports, which are delivered to every client via trailers in every gRPC response. So what it means that every client now has a coherent view about server utilization for all servers it is connected to. Then what WRR does, it calculates so-called cost per request function, which I simplified it a bit, but in an essence it's just CPU divided by QPS, and QPS is queries per second. And the reason why this metric was chosen because it represents the inherent parameters of the server, like basically how powerful your server is. But if you ask whether WRR can help us to mitigate the impact of random subsetting on server-side load imbalance, the answer is no. And it is no because cost per request function is stable no matter how many connections a given server receives. So we need to try something else. So all those conversations about deterministic subsetting and usage of WRR happened exactly a year ago here in Sunnyvale during last gRPConf, and I was a bit upset because it looked like we don't have a good path forward. So what I did, I just started talking to different people and asking them, okay, how do you deal with subsetting in your infrastructure? And one very interesting idea that I was suggested is to use proportional integral derivative controller, or PID for short, to mitigate the imbalance generated by usage of random subsetting. So what is PID and how do we use it? So basically what we did, we just forked WRR load balancer, and then we replaced waste generation part. You remember this part which was using cost per request function. We replaced it with PID. So what PID is doing, basically, it's a mechanism that is using a feedback loop to minimize real-time errors, the difference between desired state and current state. So in order to calculate the error, we use the difference between current server CPU utilization and the mean utilization. So basically, we converging all CPU utilization to the mean. We used existing WRR load reports mechanism to provide us feedback loop, and we implemented a very simple procedure to convert the output of PID into WRR weight. So I don't want to get into mass of PID too deep, just to give you a very brief overview, but basically output of PID is a weighted sum of three components. And when I say weighted sum, means that we multiply every component by a special weight, and I will refer to them as gains, like proportional gain, during later part of my presentation to avoid confusion. So what those three components are? The first one is proportional, which is the main one. It's basically the difference between current and design state. The second one is integral, which allows you to take some history into account. Basically, if you increase your input and you observe that the effect on the output is too small, it would make sense to increase your input more next time. And the derivative one has the opposite effect. So if you increase your input and the effect on the output is too sharp, so it wouldn't make sense to slow down increase, because you are risking to get oscillations and overshoot if you don't do that, even if you don't reach your target value yet. So in a sense, increasing proportional and integral gains speed up conversions and but have higher risks of overshoot and oscillations, and increasing derivative component has the opposite effect. So I mentioned that we have a simple process to convert the output of PID to WRR weight. And you can see the pseudocode for this on this slide. So basically what we did, we just start with weights equal 1, and then when we receive positive output from PID, we slightly increase the weight. And if output is negative, we decrease the weight, and we do this proportionally to the absolute value we get from PID. While working on this, we discovered a few important takeaways. So the first one is that load reports must be smooth, and the reason is that if they are not, the mean value measured on the client might be spiky or oscillating. And trying to converge to a spiky or oscillating value doesn't make any sense. So what we did smoothing using moving average window algorithm on the server. And in theory, we can do this on the client as well, but doing this on the server gave us access to the full CPU distribution, so the smoothing can be done a lot more accurately. So the second takeaway is that updates between PID and WRR weights must be synchronized. And this point requires a little more clarification. So how WRR works is this. So whenever it receives a load report from any server, it immediately recalculates the weight for this server. And it can do this because in WRR, weight updates are completely independent from each other. It doesn't maintain any state. PID does maintain state. And if we do something like this, PID updates and WRR weight updates can get asynchronized. So I didn't mention that WRR has also a background process that applies weight once in a while by default. And if we do this, then we can get unsynchronization, which is something we want to avoid. The third takeaway is that we must clump weights. If we don't do this, in cases when just a few clients using PID, the cumulative effect that they can generate is too small. So weights can naturally go up to infinity and down to 0, and we just set max and mean value to avoid this. So this table summarizes all tunable parameters we have for PID. So I already mentioned proportional and derivative gain here. So we tune them in a way to be on the safe side. So we kind of sacrifice conversion speed a little bit because we can easily tolerate conversions in order of seconds or even minutes in some cases. But we want to minimize probability of overshoot on oscillation. We use default WRR weight update period of 1 second, which is fast enough for us. We set our default subset size to 10, which is small enough value, so we are confident this is not going to give us excessive overhead from too many connections, but at the same time, PID has the flexibility to shift load within given subset. And we tune moving average window, which is a smoothing parameter. We set it to 1 minute basically by observing CPU graphs with different moving average window size on real servers we have. So here you can see some results, and by looking at this graph, you can easily say at which moment of time PID was applied, and as you can see, the effect on the server side load imbalance was huge. So in the end of my presentation, I want to briefly mention next steps. So how do we plan to use subsetting to further drive reliability in our organization? So let's consider the following use case. So suppose you have a lot of servers and one of those servers is misbehaving. So you want to avoid sending too much traffic to it, but how can you detect this from the client side? And if you use just plain round robin, the answer is that you need to take a few full round trip across all your servers, doing them in round robin fashion to detect this failure, which is too slow. So subsetting helps you to reduce this time a lot because we can use much smaller subsets, and now we can efficiently use gRPC features such as outlier detection. So we can detect bad hosts very fast, and then we can send a smaller amount of traffic to the bad host or hosts that generate high latency. So now let's revisit our goals that we set for ourselves. So I can claim that just random subsetting is already a useful enough feature. It provides a lot of benefits for many applications, but it requires developers to understand some trade-offs. At the same time, combination of random subsetting and PID, accordingly to our experimentation, is a strict improvement over round robin. So what we are doing right now, we are in the process of applying this by default and basically transparently replacing round robin with a combination of PID and subsetting, which should give us the benefits I talked about before. I also can mention that providing generic features is the goal that is very well aligned with the goals of gRPC community and gRPC maintainers. So we submitted 2 gRFCs, one about random subsetting and another about PID, and the first is already merged. The second one is still under review, but didn't get any blocking or negative feedback yet. I can say that going through this gRFC process slows down us a lot because we need to spend a lot of time and efforts discussing different features, but at the same time, it really forces us to think about generic features and come up with a design that is a lot better that we could come up with otherwise. So that's it for me. We'll be happy to answer all the questions.
So thank you for the talk. So I'm far from an expert on subsets, but I've been reading a little bit. There was a paper that came out of Google in 2022 that talked about the Rocksteady algorithm. Wondering how that compares, because it doesn't like mention the PID or anything. Wondering if you evaluated it and it wasn't doable in gRPC, or it actually isn't as good an algorithm as what you did.
So, yeah, that's a great question. I can get back here to my slide where I talked about deterministic subsetting. And the second paper is actually is the one mentioning Rocksteady subsetting. So this is one example of deterministic subsetting. And we actually implemented proof of concept for it. But yeah, the outcome was that this is not something we can add to gRPC by default.
Okay.
For the reasons, yeah, I explained here, because it's like...
Excellent. Thank you.
Yeah.
Can you briefly touch upon the benefits that this overall subsetting strategy brought for your projects in terms of, say, monetary benefits or the resource utilization?
So basically here, when I talked about problems with round robin, so those are the problems we are trying to address with subsetting. So basically resource overhead. Like number of connections reduces significantly if you use subsetting compared to round robin. So combination of random subsetting plus PID actually help us to address the second problem here, which is like, with round robin you get perfect request distribution, but load distribution might be different across server, and PID help to address this part, so it uses smaller number of connections and resulted in better load distribution. So server owners can scale down their deployments because load distribution is more tight. And last one is that something I mentioned in the end of my presentation, which is like better observability on the client side, so we can have high fidelity metric on the client side, so we can detect bad hosts, which is something we plan to use to drive reliability.
Thank you. This is regarding the PID values that we were showing. I guess the I value was probably 0 in your case. The question that I have is, how did you iterate for the P? I think 0.1, I probably 0, and D was 1. How did you iterate to get the right values for your project?
Basically, this is more trial and error approach. Like there are mathematical models how to tune your PID. Applying those models in practice, it's kind of hard, and for this particular problem, it's twice as hard because PID is applied in a distributed way. So it's not a single PID controller, it's thousands of PID controller deployed to multiple applications. So the main property we're trying to preserve is to make sure we're not getting oscillations. And we kind of, the first value we tuned is this server-side moving average window, which makes our load smooth. So once we get this smoothing parameter, we can guarantee that during, like, for example, 1 second, the average value as measured on the client will not change significantly. And then if we know this value, we can tune proportional and derivative gain in a way that guarantees that during some amount of time, we can guarantee how fast weights on a given client can change. And then we tested it out with both synthetic benchmarks and real application, and then we graph the changes of weights, and we see that, okay, indeed, our weights as tested by multiple applications, they just converge but never oscillate.
It's part of gRPC, and if anyone wants to use it, they will need to follow the same process and follow the best practice that you have done. So would some of your work be available for the community if they want to use this PID with gRPC?
I don't think it's they need to follow the same process because this kind of tuning need to be done once. This is our assumption. So the value we came up with actually proved to work for different applications with different like request profile, error rates, whatever else. And as I mentioned before, we are kind of on the safe side. So we even increase our parameters to kind of sacrifice conversion speed a little bit. So the claim we want to make is the defaults we came up with should be applicable for like, I don't know, 99% of applications. And if there is an application for which conversion speed is critical, then yes, people need to tune it themselves, but it's really not the goal for most applications because like they can easily tolerate some amount of imbalance on the server load utilization.
One of the cons shown for the random subsetting was the high connection churn. In the final state, are you still fine with the connection churn? Or?
So the connection churn part, let me get back here. So this part is completely, like almost completely eliminated by using rendezvous hashing. So the end products that we have using a combination of random subsetting with rendezvous hashing plus PID. So kind of this addresses the problem, and it's like our connection churn is very low after we apply this.
I have a different question. So like, if I understand right, you have to deploy a PID controller for like maybe per application or like for a bunch of applications. I'm curious how the deployment cost of having this new controller compares to the server load and the server resource savings that you saw from the improved load balancing algorithm.
When you say deployment cost, what do you mean? The time we spent to kind of migrate applications, or what exactly?
Oh no, I mean, I assume the PID controller too needs like CPU and resources to run, which you're saving from the server load, but you're bringing up these controllers for the subsetting. I'm curious if the costs compare or it's an order of magnitude.
Yeah, so basically the question is about the overhead of PID. Yes, and this is a great question. So basically the overhead of PID directly depends on how often we recalculate the weights. Because the PID calculation itself, like measuring like proportional component here, is a single operation, and like for derivative and integral part, it's really like, I don't know, two mathematical operations. It doesn't really matter in the compared to other expensive things like protobuf serialization. It's not even noticeable at all. The most expensive part when using PID and WRR, because PID is based on WRR, is this weight update part when we need to log things and kind of apply weights. And you can directly tune this impact by changing, let me get back quickly to this slide. Yeah, here. So there is a weight update period, which is specific for both PID and WRR. And we use default WRR value, which is 1 second. And this is proved to be like super low overhead. I didn't hear about anyone complaining of overhead of this operation. But even if it does, you can still like set it, I don't know, to 5 seconds or 10 seconds. You have control over it.
Makes sense, thank you.
One question around the same context. So about the WR and this PID weight update, you mentioned that lesson learned from your journey, you synchronize these two steps. And I was wondering what disaster can happen if you do not. Is it just delay of the weights update, or it's a data corruption, etc.?
So it's not like data corruption. It doesn't affect the requests or anything. But what happens and what we observed while doing experimentation is this. So PID receives a load report and sees that, okay, for a given server, I need to increase the weight because this server should really receive more requests. So PID does its calculation, updates the weight, but this weight is not applied. Next report comes up for the same server, and PID does it increase again, but the actual weight that is used by the load balancer is not affected. And so what it results in practice is a little bit more of oscillations, like PID can end up overshooting its internal state compared to the current state of WRR. And our fix for this was really simple. So what we did, we just ignored load reports if we cannot apply them immediately.
I have a question. So I'm wondering about the trade-off of speed of convergence. Is this sort of a property that we want to preserve for PID, or is there, like if I'm thinking about I want faster convergence, is this in service of better tail latencies, or how do I think about this as sort of a service owner? I know we don't want to tune these things, but how do you think about those things?
So the speed of convergence is important in the following scenario. So suppose you're like when you run a benchmark, you just start your server and start all your clients, and then your clients use deterministic random subsetting, and the initial state is very imbalanced. So how fast you go from imbalanced to balanced state is the property we care about. And in real life, this event happened almost never, because like real servers like run continuously. We never like really restart them. But this might have some importance when traffic patterns change. So I don't know, a given client is restarted and it picked a different subset which result in some form of imbalance. Okay, so how fast we get to the state that is balanced?
Oh, we are running out of time. That's the question. Okay. Yeah, let's take the discussion outside. Yeah, and close this up. Yes, thank you.
Thank you, everyone.